Long time no video. Today we're going to do section 11.6. It's all about radical expressions. So let's define what that is. A math expression using a square root is known as a radical expression. The radical sign is the symbol that we use, and it's the square root symbol along with like the cube root and the fourth root, but we're just going to focus on the square root in this class. The number underneath the radical sign is called the radicand. So this x down here is our radicand of that problem. So your radicand may contain numbers, variables, or both. It may contain one or more terms or more than one term. What we're going to be doing is calculator lists. We're going to simplify things without getting the messy decimals, and we're going to simplify things with variables in them that we can't type into our calculator. So when seeking the square root of something like x squared, you can ensure the answer will have the correct sign by using absolute value signs. And this is just something that's kind of understood, but we have to define it first. So if we take something like the square root of x squared, our answer is just plain old positive x. So if you take the square root of like 2 squared, we assume that it's just positive 2, because if we plug in negative 2 and square it, when we take the square root of this, we're really taking the square root of 4, and we just assume that it's positive 2. So something kind of unwritten, and if your answer is negative, that means that the negative sign was on the outside. This is like negative 1 times the square root of x squared, and that can give us negative 1 times the absolute value of x, or the positive answer of x. So we assume this from now on. We don't need to write any more absolute value signs. But let's do some problems. If you have something like x cubed and you want to take the square root of it, x cubed really means that you have x times x times x. And a square root is kind of like jail, where you can only leave if you are something squared, or if you have a friend to leave with. So like these x's right here have a partner to leave with, so they can leave the jail. So we took one pair of x's out, and we ended up with one x inside that can't leave. Because we could have wrote this as the square root of x squared times the square root of x. Same thing, so we get this for our answer. Now x to the fourth we could rewrite as x times x times x times x, or we know that it's x squared times x squared. So x squared times x squared means that we have 2 pairs that can leave. This x squared is a pair, and so is this one. So we end up with x squared on the outside. You could have also written this as x squared squared on the inside. Take the square root of a square, they undo each other, and you're still left with x squared. Now the next ones, hopefully you've caught on to the pattern. If you have 5 x's, that means that there's only a couple of them that can be taken out. You can make a pair here that can take out, and a pair here that can be taken out. And then there's one lonely x that doesn't have a friend, so he has to stay inside. So the square root of x to the 5th is really the 2 pairs of x's we took out, so x squared, times the square root of x. So the next one, x to the 6th power, we can make 3 groups of x's, so it's x cubed. X to the 7th power, we could make 3 groups, like the x to the 6th, and then there'd be 1 x left inside without a friend to leave. So here's some more examples that we can do. And then we're going to learn some rules that we've already kind of been using, but actually put them into rule form. So A, we have x squared plus 8x plus 16, and we're taking the square root of all of that. We can't split this up because it is 3 terms on the inside here. So we can't just say, well, the square root of x squared is x, and then take the square root of 8x, and then take the square root of 16. Instead, what we have to do is write these as squares on the inside so that we can take the square root. So let's factor this. X squared plus 8x plus 16. If I want 2 numbers that add together to make 8 and multiply to make 16, my numbers are 4 and 4. So this could be written as the square root of x plus 4 all squared. And remember, squares and square roots undo each other. So if those cross off, we're just left with x plus 4. We can do something similar with b and c. Hopefully when you look at the square root of 9 over 49, you notice that 9 and 49 are perfect squares. There's something we should know the square root of off the top of our head. But when they're in a fraction like this, we can split them up into the square root of 9 on the top, divided by the square root of 49 on the bottom. Square root of 9 is 3, and the square root of 49 is 7. So the square root of 9/49 is 3/7. And if we take a look at the one on the bottom, you notice that 3 and 75, neither of them are perfect squares. So we can't do what we did with b. But let's see if we can simplify it first. 3 over 75 can be simplified into 1/25. The fraction is exactly the same. And now these numbers should make you happy because the square root of 1 is something nice and pretty, and so is the square root of 25. Square root of 1 is just 1. And the square root of 25 is 5. So the square root of 3 over 75 is really just 1/5. And you could type this in your calculator, and for that one you'd get out like 0.2. You would get 1/5 out in your calculator, which is good, but from now on, no calculators with this stuff. So now here's our rules that we just basically did. We're going to do one with multiplication and then one with division. So the multiplication property says that we can do two different things. We can either take two numbers and multiply them together underneath the square root, and then take the square root of whatever that number is. So like 4 times 25, we could do 4 times 25 first, and then take the square root of what we have. Or we can split it up into two square roots. So the square root of 4 times the square root of 25. We know the square root of 4 is just 2, and then the square root of 25 is 5, and we still get 10. So this works forwards and backwards, and you use whatever one you need to in order to break it up into things that you know the square root of. So number A, or letter A, if I want to do the square root of 3 times the square root of 12, I look at my numbers, and neither of them are perfect squares. So I want to combine them to see if I get something that I can simplify. 3 times 12 is 36. And now the square root of 36 is something that I know, so I can just take the square root of it. And we get 6. And if you type both of those things into your calculator, you will end up with 6. Now 24 is a little strange, because 24 is not something I know the square root of, and it's not something that can be broken up into two perfect squares. So let's think of at least one perfect square that it could be broken up into. 24 has a perfect square of 4 in it, and then a 6. So we could write this as the square root of 4 times 6, all underneath the radical. And then we could split that up into two radicals, the square root of 4 times the square root of 6. And I know the square root of 4 is 2, and since I don't know the square root of 6, I'm just going to leave it as the square root of 6. We want to double check that we can't break 6 up into any more of our perfect squares, and no more perfect squares fit into it. So this is our answer. This is in simplified form, 2 root 6. It's an exact form, we're not getting a decimal out, but it is as simple as it can be. We have a division property, or a quotient property, that's almost exactly the same. It says that if you have two things underneath the radical, you could simplify them first, like this one we got 9, and then take the square root. Or you could take the square root of each individual part and then divide whatever your answer is. And you should end up with exactly the same answer. So if we take a look at the very first one here, the square root of 5 over 4. Now that can't be simplified. We'd get a decimal if we tried to change it into anything else, and we don't want decimals. So then we're going to split them up into the square root of 5 on top, divided by the square root of 4 on bottom. Square root of 5 can't be simplified, so we're just going to leave it and not get a decimal answer. But the square root of 4 is something we know. It's just 2. So square root of 5 over 2 is a simplified form of the square root of 5/4. The next one is a little different because we can simplify something first. If I have 3 m's on the top and a 9 and only 1 m on the bottom, we can get some of our m's to cross off. Think back to those exponent rules we did forever ago. We subtract 3 minus 1 and it'll give us 2. So this is really m squared over 9. And now these numbers should make us happy because the square root of m squared is really just m, and the square root of 9 is really just 3. So we couldn't have done this if we would have tried to break it up first, because then we would have had the square root of m cubed on the top, which wouldn't have gave us a perfect square, and then the square root of 9m on the bottom. So sometimes it's easier to simplify things first and then split them up, and other times, like this first problem here, we need to split them up first and then simplify. So now let's put all of this together. Number 4 says using the product and quotient properties together. So we're going to have to do more than one thing with all of these. So if we take a look at problem A up at the very top, it says the square root of 80 divided by the square root of 25. Now we could simplify that, but a number that goes into both of them is 5. And 5 goes into 80 a weird number of times. It's not a perfect square. And 25 already is a perfect square. So for a problem like this, it makes sense to break it up first, to get the square root of 80 divided by the square root of 25. And then the number on the bottom becomes a nice pretty 5. The square root on the top, though, is not finished, though. We need to think about 80 and think about if there's any perfect squares that go into 80. And if there are, we need to find the biggest perfect square that goes into 80. So chances are 4 popped into your head, but is there a number bigger than 4 that goes into 80? Well, instead of just trying these over and over again, we could make something that we call a factor tree. And treat this just like the variables we did in the very first slide. You need a partner to leave. So let's break 80 up. You can break it up into anything you want. We could do like 8 and 10. And then if you break up 8, you get 4 and 2. And then 4 can be broken up. And if you break up 10, you end up with a 2 and a 5. And then if we look at all of our numbers on the end, remember you need a friend to leave. So these two 2's can leave together, and these two 2's can leave together. But that 5 doesn't have any friends, so he has to stay on the inside. So we took out one group of 2 times another group of 2, and then we still have 5 inside the square root. So we would simplify that outside to 4 root 5, all divided by 5. Now be very careful that you don't divide the square root of 5 and 5, because they look the same, but one's underneath the square root. So we can't mess with things that are on opposite sides of the square root. Remember, it's like being in jail. If you're in jail, don't hang out with people on the outside, and if you're on the outside, you don't hang out with the people on the inside. So we can do the same thing for B. Square root of 4 times x to the 5th, all divided by 9. So your numbers, 4/9 can't be simplified, but they're perfect squares, so that makes us happy. On the top, we could write it as the square root of 4 times x to the 5th. And on the bottom, we'd have the square root of 9. And then we have a couple things going on here. We could break up the top even further so that we have the square root of 4 times the square root of x to the 5th, all divided by the square root of 9. And then we could simplify our perfect squares. The square root of 4 is just 2. X to the 5th means that you have 5 x's there. And you can make 2 groups that can leave, so x squared is on the outside. And one poor x is stuck all alone on the inside. And it's all divided by the square root of 9, which is just 3. Double check that nothing can be simplified, like your stuff on the outside, and when it can't, you are all done simplifying. Go ahead and pause the video and try these next ones and make sure you can do this stuff on your own. Alright, these are the answers I got. The first one should have been 6 times the square root of 3, all divided by 5. Second one, I got x times the square root of 10x divided by 10. And then finally C, I got 2 root 5 on the top divided by 7 times x squared on the bottom. If you did some simplifying in B before you took the square root, you would have ended up with the square root of 10 in the bottom. And we're going to learn in the next couple of days that you're not allowed to have square roots in the bottom. So if that happens right now, don't simplify first. Like I can take the square root of 100 and just get 10. And later we'll learn how to undo that if that's how the problem happens. If you have any questions on things, below star next to it, and we can talk about them in